In this lesson, we're going to look at the topic of atomic structure, or what atoms are actually made of. Now, a long time ago, people thought that if you cut up a substance, if you cut it until you cannot cut it anymore, alright, so the smallest unit of any substance, you get what is called an atom. Alright, but with advances in science, with advances in technology, people discovered that atoms are not the smallest thing that make up the universe or make up the things in the universe. Right, there are things that are even smaller than an atom. Alright, so in this lesson, we're going to learn about the particles that make up an atom and how they are actually arranged in an atom. So as mentioned, there are particles that are even smaller than an atom. Alright, and in fact there are three particles that make up an atom. They are protons, neutrons, and electrons. Okay, so the first thing that we need to learn is where are they found in an atom. Alright, protons and neutrons. Okay, protons and neutrons, they are found in the center of the atom. Alright, in a region called the nucleus. Okay, how about electrons? Electrons are found outside the nucleus. They are found in what we call electron shells. So they orbit around the nucleus in what we call electron shells. Okay, so the first thing that we need to learn, again, protons and neutrons are found inside the nucleus. Electrons are orbiting the nucleus in what we call electron shells. Okay, the next thing that we need to learn is the relative masses. So proton, if you look at the relative mass of a proton and a neutron, alright, what it means is that protons and neutrons have the same mass. Alright, and then when you compare it to the mass of an electron, 1/1840, if you look at some textbooks, they give a more accurate value of 1/1836. Now, both are equally acceptable. Right, but if you compare the relative mass of an electron to that of a proton and a neutron, you would realize that it is so much lighter than protons and neutrons. So essentially, electrons do not contribute to the mass of an atom. Okay, and essentially the mass of the atom is contributed by the nucleus. The nucleus makes up for almost the entire mass of the atom. Right, so that is the significance of the relative masses. Alright, next we look at the relative charge of each subatomic particle. Alright, protons have a charge of plus. Alright, protons are positively charged, electrons are negatively charged, and then neutrons are neutral. Okay, this is a very old joke, but I'm still going to say it. Alright, neutron goes into a bar. He orders a drink. The bartender brings him the drink. So neutron asks the bartender, how much is the drink? And the bartender said, for you, no charge. Alright, so hopefully that story helps you to remember that neutrons have no charge. They are neutral. Okay, now, so what is the significance of the charges is this. In some higher level questions, they will pass a stream of subatomic particles through what we call a charge plate. Alright, so there's a region where there is positively charged, there's a region where it's negatively charged. Now when you pass the subatomic particles through the charge plates, and then they are going to ask you what is going to happen to each subatomic particle. Now for that, you have to remember the relative charge. Now in science, we learned that opposite charges will attract and then like charges will repel. Alright, so since protons are positively charged, they will be attracted towards the negatively charged plate. Okay, and then since electrons are negatively charged, they will be attracted to the positively charged plate. Right, and since neutrons are neutral, they will not be attracted at all. Okay, now the other thing is this. If you look at whatever that I've just drawn, so neutrons, protons, and electrons, you will find that electrons seem to be deflected by a larger angle than protons. That means it moves even further away from the center line. Now, why is that so? Right, for that we need to go back to the relative masses. Alright, so imagine if you pull two people, one of them is very light, one of them is very heavy. If you pull them by the same force, what would you notice? The one that's lighter will move over a larger distance as compared to the one who is heavier. So that is what is happening here. Our electrons are so light that they are deflected. Alright, so they move away from the center line by a larger angle as compared to protons, because protons are heavier. Okay, so this is quite a common question that you will see in MCQ, which relies on your knowledge of the relative mass and relative charges of each subatomic particle. Now here are three terms that are very similar and students often get confused about them, so I'm going to clarify it here. A neutron, as we have already mentioned, is one of the subatomic particle. That means it's one of the particles that make up an atom. Alright, and what's so special about this particle is that it is neutral. Okay, so neutrons and protons are found in the center of the atom, and the region in which protons and neutrons are found is called the nucleus. Alright, it's the center of the atom, region in which protons and neutrons are found. Okay, the last term nucleon is less commonly used, but what is a nucleon? Nucleon is a general term to represent protons or neutrons. Alright, so protons and neutrons are both nucleons. So when we say the number of nucleons, essentially it means the number of protons plus number of neutrons. Okay, so nucleon is a general name to represent protons or neutrons. Now the next very important part about this chapter is to be able to determine, when given an atom of an element, how many protons, neutrons and electrons there are in the atom. Right, for that we need to first learn how an atom of an element is represented. Alright, so it's actually represented in this way. There are three parts to the representation. X represents the symbol, so it tells you what element are we looking at. Alright, Z is the proton number, it's called the proton number, or sometimes we call it the atomic number. And then A is the mass number, or sometimes we call it the nucleon number. Alright, so if I have an atom of carbon, for example, I can represent it like that. Okay, where C is again the symbol, and then 6 is your atomic number or proton number, and then 12 is your nucleon or your mass number. Alright, so what can we tell from the symbol, the numbers? From the proton number, we can tell the number of protons. Alright, that's why it's called the proton number. Alright, in an atom, since atoms are neutral, that means that the positive charge is cancelled by the negative charge. So for any atom, the number of protons must be equal to number of electrons. Alright, and then how about neutrons? Neutrons, we need to look at the nucleon number or the mass number. Alright, I've already mentioned nucleon represents protons and neutrons. Alright, so nucleon number tells you the number of protons plus number of neutrons. Alright, since we already know number of protons from the proton number, we can therefore then find the number of neutrons. So in the example that we have seen in carbon, in an atom of carbon, number of protons would be 6, number of electrons would be 6. Then number of neutrons, how do we find number of neutrons? Is to take the nucleon number minus the atomic or proton number, so it will also be 6. Now one thing that I want to highlight, especially highlight over here, is that this representation that we have just learned is to represent an atom of an element. Alright, this is not the same as what you see in a periodic table. Alright, so for example, what you see in a periodic table, for carbon you may see something like this, and then you have 6, and then you have 12. Alright, so students will get confused. Hey, so why is this different from whatever that we've just learned? Now the representation in the periodic table it represents the element, alright, not a particular atom of the element. Alright, why do I say that? Now yes, in the periodic table, the smaller number that you see is also the atomic number. Okay, but the larger number that you see is not the mass number, is not the nucleon number. It is what we call the relative atomic mass. Alright, this is something that we're going to learn in more concept, but essentially it is the average mass of all the different types of atoms. Alright, so this is the reason why students often get confused is that because this number, alright, is often the same as the mass number. Right, it's often the same, but it is not the mass number. Alright, why do I say that? Now let's look at this particular example of chlorine. Right, chlorine, if you look at the periodic table, you will see something like this. Alright, so if you look at the bottom number, 35.5, if you treat this as the mass number, if you treat this as the nucleon number, it wouldn't make any sense, because that means that you have half a neutron. How is that possible? How can you split a neutron? Alright, so this is where the confusion comes in. Now if you were to recall that this is not the mass number but the relative atomic mass, that means it's the average mass of all the different types of atoms, then it will make sense, because when we take average of something, sometimes we can end up as a decimal. Alright, now I have mentioned this a few times, average mass of different types of atoms of an element. So you may be wondering now, why would an element have different types of atoms? Now I'm going to show you now using the example of chlorine. So if you analyze a sample of chlorine, you may find one particular type of chlorine atom which has this particular composition. Okay, so let's practice our use of the two numbers. From the representation of the chlorine atom, we know that there are 17 protons and 17 electrons, and then to find number of neutrons, we need to take the mass number minus the proton number, which will give us a value of 18 neutrons. Okay, now if you again analyze a sample of chlorine atoms, you may find that there is another type of chlorine atom which has a slightly different composition, right, which can be represented like this. Once again, this second type of chlorine atom has 17 protons, 17 electrons, and 20 neutrons. Okay, so if you analyze these two types of chlorine atoms, what is apparent is this, that they have the same number of protons but they have different number of neutrons, and atoms of the same element with the same number of protons but different number of neutrons are given a special name. Alright, what is the special name? We call them isotopes. Okay, so how do we end up with 35.5? Is that because we take the average mass of the two. Alright, those of you who are faster, if you are taking 35 plus 37 divided by 2, that is not correct, because they exist in different percentages. Right, we will look more into that when we go into more calculations. Okay, as mentioned, atoms of the same element with the same number of protons but different number of neutrons, they are called isotopes. Alright, so chlorine 35 and chlorine 37, alright, they are actually isotopes. Okay, now based on the fact that they have different number of neutrons, and we know that neutrons and protons contribute to the mass of the atoms, what it means is that isotopes will have different masses, right? Atoms of the same element, but their isotopes will have different masses, and the mass of an atom can affect what we call the physical properties. Physical properties like melting point and boiling point. Alright, so we need to remember, due to the difference in masses, isotopes actually have different boiling points, slightly different boiling points and melting points. Okay, however, they have the same number of electrons. Now, in most chemical reactions, it's the electrons, or more specifically the valence electrons, which we will learn in a while, that is involved in chemical reactions. So when we have the same number of electrons, we will end up with the same number of valence electrons, meaning isotopes will actually have the same chemical properties, meaning they will undergo the same type of reactions, they will form the same type of compounds. Alright, so as mentioned in the last slide, isotopes have the same chemical properties, meaning they undergo same reactions or they form the same type of compounds. The reason for that is because they have the same number of valence electrons. Okay, what are valence electrons? We're going to learn them in the next slide. But they have different physical properties. Why? Is because they have different masses, and physical properties are influenced by the masses of the atoms. Now, the last part of atomic structure, we need to learn something called electronic structure. Alright, sometimes electronic structure is also known as electronic configuration. Alright, what does it mean? It means how electrons are arranged in atoms. Okay, now very early on, I've mentioned that electrons actually orbit the nucleus in regions where we call electron shells. Okay, so if we look at an example, magnesium over here. Again, magnesium, an atom of magnesium can be represented by the following two numbers, right? And the smaller number, or the atomic number, tells us that we have 12 electrons in magnesium. Alright, so how are these 12 electrons arranged in electron shells? Are they all crammed into one electron shell? Now the answer is no. Right, there are multiple electron shells in an atom. Alright, so for example, magnesium. So at the center you find the nucleus, where it contains protons and neutrons. So your nucleus is essentially positively charged. Okay, the shell that is closest to the nucleus is shell number 1. So the next outer shell is called shell number 2, and then the next outer shell is called shell number 3. Now, to know how electrons are arranged in electron shells, we need to learn this, that electron shell number 1, right, can only have a maximum of 2 electrons. Okay, electron shell number 2 and onwards can have a maximum of 8 electrons. Alright, so for the case of magnesium, it has 12 electrons. How are these 12 electrons going to be arranged in electron shells? Is that the first shell will have 2 electrons. How about second shell? We can accommodate 8 electrons. So now we already have 10 electrons that are occupying the electron shells. How many electrons do we have left? We have 2 more electrons. Alright, so if you look at the diagram there, in an atom of magnesium, we have 2 electrons in the first shell, 8 electrons in the second shell, and 2 remaining electrons in the third shell. Okay, a few important terms to remember. The outermost shell, the outermost electron shell is given a special name. It is called your valence shell. Okay, and the electrons that are found in the valence shell, meaning the outermost electrons, are also given a special name. They are called your valence electrons. Alright, so when we were talking about the similar chemical reactions or the same chemical reactions that isotopes can undergo, why is because they have the same number of valence electrons. Now in chemical reactions, it is these valence electrons that are involved in bonding. Alright, they are involved in chemical reactions. So the number of valence electrons would affect the type of reactions that they can undergo. It will affect the type of compounds that they will form. Now there are two ways to represent the electronic structure, electronic configuration of an atom. One way is by drawing out the diagram that is shown here. The other way is to represent it by a series of numbers like this. Alright, so the first number represents the number of electrons in shell 1, followed by shell 2, and then shell 3. Alright, in this case, shell number 3 is also your valence shell. Alright, so we know from the series of numbers that there are 2 valence electrons. Now let's take a look at the electronic structure of the first 20 elements. Alright, take some time to look at the arrangement of electrons and see whether you can spot any patterns, any trends. Alright, but before that, just again a reminder, vertical columns in a periodic table is called group, whereas horizontal rows are called period. Alright, now again, take some time to see whether you can spot any trends. Now, if we look at elements in the same group, for example, group 1, okay, can you spot any trend or can you spot any pattern? Right, I hope you can see that all the elements in group 1 have 1 valence electron. Okay, check for the other groups. Right, you'll find that the group number, okay, the group number actually tells you the number of valence electrons. How about period? Now if you compare the elements from lithium all the way to neon, now what is one similarity with the electronic structure? You will find that they all have 2 electron shells, 2 occupied electron shells. And then if you look at elements in period 3, you will find that all the atoms have 3 occupied electron shells. So essentially your period number, it tells us the number of electron shells that are filled. Alright, now we can use it in the reverse manner. That means given the electronic structure or electronic configuration of an atom, we can tell which group and which period the element is found in. Alright, so for example, now if we ignore the periodic table, without looking at the periodic table, let's look at chlorine again. Alright, chlorine has the following number, following proton and mass numbers. So for that, we can tell that chlorine has 17 electrons, which will be arranged in the following electronic configuration, 2.8.7. Okay, so this is the electronic configuration for chlorine. Now based on that, we can tell that there are 7 valence electrons, meaning chlorine must be found in group 7. Okay, and then if you look at the string of numbers, there are 3 numbers there, 2.8.7. Now what it means is that there are 3 electron shells that are filled. So that tells us that chlorine must be found in period 3. So as what we have deduced in the last slide, the number of valence electrons in an atom of an element tells us the group number in which the element is found in. Alright, and the number of shells that are filled tells us the period number of the element. So that's all for atomic structure. Again, there are four very important parts. First, we need to remember the type of subatomic particles that are present. Where are they located? What is the relative mass? What is the relative charge of each particle? Next, we need to learn how to interpret the representation of an atom of an element based on the numbers given to find number of protons, neutrons, and electrons. Third thing is to recognize what is an isotope or what are isotopes, and how would the difference in the type of atoms affect the chemical and physical properties. And lastly, we learn about electronic structure or electronic configuration, which how electrons are arranged in an atom.